Welcome to this decarbonization showcase hosted by NYSERDA's Empire Building Challenge. Its purpose is to familiarize you with technologies and strategies to facilitate decarbonizing our building stock. All sessions will be recorded and posted to the EBC Showcase Series website. Each presentation will be 20 minutes, followed by 10 minutes in which the presenter will respond to your questions, which you can post in the webinar chat. And now it is my pleasure to introduce Tom Sottile of Sunamp.
Good afternoon, Sal. Thank you so much for inviting me here today. My name is Tom Sottile, and I am the U.S. General Manager for Sunamp. Sunamp is a world leader in thermal storage technologies using phase change materials. Why do we need storage technologies? In our quest to decarbonize our electrical power, we will be adding more renewables to the grid, and this will create an imbalance between generation and consumption. Storage can sit in the middle and help balance that out. Sunamp was formed in response to climate change in 2005. Our CEO, Andrew Bissell, actually came out of retirement and wanted to try to help do something to mitigate climate change. He lives in Scotland, so our headquarters are in Scotland, and that is where our factory is. He decided that storage would be necessary, realized that storage should be necessary, and decided to focus on thermal storage because there had been quite a bit of innovation in electrical storage recently and not much work done on thermal storage. However, 40% of the energy we use thermally, either for heating, domestic hot water, or cooling. Thermal storage has a lot of advantages over electrical storage, but the largest being that it is much less expensive than electrical storage, about 1/3 the cost per kilowatt hour. It has a longer lifespan. We can recover the energy immediately to serve thermal outputs. It's made from sustainable supply chains, non-flammable, and non-toxic. Thermal storage traditionally was done with sensible heat in large tanks of water. With the exception of ice, ice is the original phase change material, but it's at the wrong temperature for domestic hot water or heating. We've been working with a salt hydrate that has 4 times the energy density using its latent energy storage than water. We didn't invent the salt hydrate. It had been around for a while, but it had 2 principal challenges that really made it difficult to commercialize. The first was a very poor cycle stability. We have solved that problem, and we have been tested independently for 10,000 cycles, and we have an A rating, which means less than 5% degradation. We've tested it in-house for over 43,000 cycles. So at 2 cycles a day, that is changing from a solid to a liquid, and then from a liquid back to a solid twice a day. That's over 50 years, and we still have less than 5% degradation. So now we think we have a product that we can use for a very long lifespan. The second issue or challenge is that the phase change material tends to be a better insulator than conductor of thermal energy. So we need to develop a very high power heat exchanger that can recover the heat from the phase change material instantaneously in a way that we can raise the incoming water from 40 degrees Fahrenheit up to 130. Solving these 2 problems led to the commercialization of our products that we call thermal batteries. Up in the left-hand corner, you see a salt hydrate raw material. It's the same salt that's on your potato chips. And we put that in a mixer with water and our stabilizer, and we pour it into those red polypropylene boxes. All of the components of the phase change material are listed by the FDA for human consumption. You see 4 pipes coming out of the top of the box. That's 2 independent heat exchangers that can act as a plate exchanger, heat exchanger, meaning that we can charge and discharge the battery simultaneously, or we can charge it, store the energy in the phase change material, and then consume it later. We have different phase change materials at different temperatures for different applications. But our main product is what we call our P58 that changes phase at 58 degrees Celsius or 136 degrees Fahrenheit. We can put those different phase change materials into different size boxes to customize the storage solution. Thermal energy, thermal storage is an integrator technology. It can work with many different inputs. We like to charge our thermal batteries using our high power heat exchangers with thermal energy, either from an air to water heat pump, a boiler, a CHP, waste heat. On the cold side, we would use a chiller. Our residential models do have small 2.8 kilowatt electric heaters that can take immediate advantage of renewable energy or time of use electric. So here is just a picture of our thermal battery, a 60-gallon equivalent to a 60-gallon tank. Besides the remarkable difference in size, some of the other advantages are a greatly reduced heat loss, about 25% of what the tank is, meaning that we can store the water 4 times as long. We can store the energy to create the water 4 times as long. There's really not much water in our battery, less than a gallon. So we've eliminated the burst potential that you would have with the tank. This is very important in multi-level high rises. We've also greatly reduced any risk of Legionella, and our life cycle is probably 3 to 4 times that of a cylinder. I'm just going to run through some quick examples to demonstrate how the thermal batteries are applied. This is something we've replicated in the UK many times. It's what we call a tower block, multifamily apartment building, where traditionally they had condensing modulating boilers in each apartment. Those were removed and a geothermal loop was put in, brought up through the building, where we use small water to water heat pumps to pull the energy out and store it in our thermal batteries. The combination of the two allows us to meet peak demand with a reduced size heat pump that we can operate on off-peak hours. This is a project that we're doing with NYSERDA on the Empire Building Challenge. This is a multifamily 6-unit apartment building in Brooklyn, where we took out the gas-fired boiler. We're using 7 of our what we call Thermino 80s. Each one can store about 50,000 BTUs. We're using the electric heaters that are immersed in the PCM to charge these with overnight low electric rates, and then discharge them during the day for both heating and domestic hot water. This is just an example of pairing it with CHPs. The capstone generators are creating electricity and heat. Sometimes generation outpaces consumption. At that point, we store the heat in the batteries. We store the excess electric in electric batteries. When consumption outpaces generation, we discharge the two. We can also improve the efficiency of gas-fired equipment. This is a project we did with NYSERDA under a technology transfer grant, where we measured the gas consumption to produce hot water and the cycle rates using a standard Wall-McLean Ultra boiler, condensing boiler, with a standard indirect tank. We replaced that with our thermal battery, and we compared the cycles and gas consumption. We showed a 50% reduction in the amount of gas consumed to produce the same amount of hot water. This is attributed mainly to the reduction in cycle rates. The blue is every time the boiler fired on the indirect. The green is every time it fired with our thermal store. Latent energy will discharge at a constant temperature as the material is converted from one phase to the other. This constant temperature will keep the boiler off for longer periods. When the boiler does come on, it runs for a much longer time. It has a low return temperature, which promotes condensation and increases efficiency. Another project we did under the NYSERDA grant is where we had a 200 apartment building in Troy, New York, where they have a geothermal system to do heating and cooling in the building, but it's not sufficient to provide the peak demand for hot water. So they have 3 gas-fired water heaters. We use a standard water-to-water heat pump, 410A, so it can only reach about 120 degrees. So here we're using a cooler PCM that actually melts at 110. And we're taking energy out of the loop. In the summertime, this is improving the efficiency on the cooling side. We're storing that energy up and using that as a preheat to the gas-fired water heaters. And we found a 50% reduction in the amount of gas consumed by doing this, because the gas heaters are now only heating the water from 100 to 140 instead of from 50 to 140. So in summary, thermal storage is a way to reduce peak demand. It's also a way to time shift when the energy is consumed, and it is a great way to recover waste heat. Using PCM materials is just more efficient, effective way of doing that. So at this point, I'd like to open up the webinar to questions.
Great. Thank you, Tom. If anyone has a question, can you please post it in the chat, not the Q&A function, but the chat function. I will be glad to read your question. What is the ideal building type / size for this technology? What are the barriers or limitations?
The great thing about this technology is it's scalable. We have heaters that can do 20 gallons that could just fit underneath a sink, or we have them in shipping containers for industrial processes. So we can customize any storage solution basically for any building. What we're looking for, again, are the three main purposes of thermal storage. That is peak shaving, to downsize the amount of generation equipment. I'll give you an example. Let's say we had a hotel in New York City that wanted to decarbonize their hot water, which is now gas fired. They don't have room for heat pumps, so they're going to put in electric flow boilers. Well, when they look at the peak demand, they realize they need 750 kilowatts of energy to meet that peak demand. But the building only has 350. So that would mean going for an electrical upgrade. However, the peak demand is only 3 hours a day for two independent or two separate periods. By combining that with storage, they can get away with the 350 kilowatts that they do have available in the building. So that's a great example of peak shaving. I mean, time shifting is pretty obvious. Waste heat recovery is something that we've been also talking to NYSERDA about, looking to find a project or a host site to demonstrate that for their heat recovery ponds.
Great. So a follow-up question, do you have any applications of this technology in hospitals, for example?
We are looking at a project right now where we are going to recover the heat from the condenser water from the AC and then store that and use that for domestic hot water. But I don't have that installed at the moment. I do have a project in Brooklyn where we are recovering heat from a data center and then using that heat to help provide thermal energy for a thermal spa, which is right next to where the crypto miners are.
Great. Another question, what mechanicals are required to integrate the Thermino with solar thermal or solar PV, and which way is best?
So solar thermal will give us a high output thermal energy. We'd love to charge our batteries with thermal energy because we've developed that high power heat exchanger and we want to take advantage of that. So really the only thing you need there is a circulator and some type of control system, and obviously the thermal panels. Solar PV is also another great way. A lot of times solar PV is more attractive than solar thermal. We can use the electric heaters that are immersed within the thermal batteries to take advantage of excess solar PV, create heat, and then store the heat and use it whenever we want.
Great. Another question, would you consider an example project where you could try waste heat?
We are looking for that right now. Host sites are sometimes difficult to find. We have a lot of applications. The one I discussed about recovering heat from the The crypto miners
Yeah.
is an excellent one, and we're looking for more where we can either recover heat from the steam condensate systems in New York, where we're just dumping that heat down the drain. Actually, we have to cool it first and then dump it down the drain. Why not take the heat out of that, store it in thermal batteries, and reintroduce it into the system? Also, recovering heat from condenser water is another great option.
Great. Any other questions? Uh, I am thinking waste heat from domestic showers is the follow-up to
Right.
that last
So I
question.
think what you'd want to do there is combine thermal storage with a wastewater recovery heat system like Shark or some of the others that are out there.
Great. Another question. Can you please highlight any applications or use cases where Sunamp might not be recommended?
Uh, hmm, that's a good question. I mean, if we're talking about thermal storage, I would recommend Sunamp. Um, we we don't have phase change materials at all the temperatures. So possibly there's a temperature where we want to recover the heat where we just don't have a phase change material that works effective at that temperature. But besides that, I mean, we're going to be a more compact system with much, much lower heat losses. So I can't imagine a situation where we wouldn't want to use a phase change material.
Got it. So only when you're dealing with really intense heat situations would it not be
Well,
applicable,
we
is what you're
have
saying.
really hot temperatures. We have one that's 285 degrees Celsius, and we're working on one that's 540 degrees Celsius. So we do have ones that can store energy to create steam. And the nice thing about us is that we're not a pressurized vessel. So you're storing the energy in the phase change material at basically an ambient temperature. When you run the water through the heat exchanger, it will produce steam. So the only pressurized area is the heat exchanger itself as opposed to the whole vessel. We do struggle with some of the ambient temperatures. We have a P28, which is about 83 degrees, but we don't really have anything in the 70s Fahrenheit. The next one that we have commercial is our P11, which is around 52 degrees. So we don't have a whole lot in that middle ambient temperature.
Got it.
But normally what we would do there is use a reverse heat pump to bump it up or bring it down, depending on what the actual use case is.
Great. Any other questions from attendees? Tom, I had a question about the Troy project. Where were the units stored? Were they in a mechanical room or were they closer to the individual dwelling units? I think you said there were about 200 dwelling units on the project. And the reason I'm asking, is there any significant difference in performance between, say, storing them out of sight in a mechanical room, say in the basement, as opposed to nearer the end user unit itself?
Right. So the project in Troy, they are for central distribution. They are located down in the mechanical room, which is convenient because we have access to the geothermal system and we also have access to the gas-fired water heaters. So it kind of just sits in the middle. There has been a lot of interest in shifting the domestic hot water to per apartment and eliminating the central systems, reducing the amount of labor and piping that goes into all of that, and then switching the load over to the tenant itself or the owner. So you'd have a residential style.
Got it. But then you'd have loss of floor space as a result, correct?
Right, but the nice thing about our product is it can fit right underneath the kitchen counter. So it can be an appliance right next to the dishwasher. So you're not
Got it.
losing that closet. Another use case that we see is that we're putting them on a shelf above the laundry. So
Hmm.
one of the projects I'm working on right now, they're specifying to use 240 Therminos, two of our 40-gallon equivalents. These are only about 28 inches high. So they can fit on a shelf above the washer and dryer. And by putting the 240s together, we can get almost 110 gallons of hot water out of it, instead of just 80, because we're able to drain that first battery below the 105-degree temperature. That's usually what we consider usable. We can bring that right down to the incoming temperature and then use the second battery to top it off.
Great. Yeah, a question came in. It sounds related to that. Can Therminos store more energy per unit volume using higher temp phase change, then add a mixing valve to generate more domestic hot water per unit volume of phase change material?
So we do have a what we call a P89 and a P85 material. Both of them have the same energy density as the P58. You will get a little extra sensible heat because it's at a higher temperature, but it's not tremendous. And they're usually not worth depending on the application. If you want a higher output temperature, then obviously you need to use those. But if you're going to blend it down back to domestic hot water, there's usually not enough value there to not use the P58 material because of the extra energy that you have to put in to get to the higher temperature in the first place.
Got it. Any other questions from the audience? Does not appear so. So, Tom, thank you very much for your presentation today. Thank you, everyone who has attended. Thank you for your questions regarding Sunamp. If you have any follow-ups, Tom's information is here on screen. Oh, it looks like, no, this is just everyone thanking you for your presentation. So thank you all, and I hope you can join us for the rest of these series, which will be taking place on Tuesdays at noon for the next coming weeks. Invites will be going out shortly. Thank you all.
Thank you for inviting me. Bye now.